Guys, let's start filling these in here. So we're talking about vectors. So quantities like length, mass, and temperature that have, anybody know what those are? Magnitude, good. That have magnitude, but not direction. Are called, do you know what those are called if it's got magnitude but no direction? Scalar, yes. Okay, and then quantities like velocity, acceleration, and force, those have both, what do you think? What were we talking about? Magnitude and direction, good. Those are called vectors. So a little bit of geometry in here, but not much. Vectors are represented geometrically by a directed line segment. You can think of it as like a ray, like it's got two ends because it has a specific length, but it looks like it's got a starting point and then an arrow showing the direction that it's going in. So what this would look like, if I draw one here. That is a vector. Most of the time you're just going to see the arrow. I'm just showing you that, look, it's a segment, but it has a specific direction. Okay? The way you're going to label this, you would call it vector AB. You always start with the initial point. And above it, it's like half a ray. So you have your line, and then you have one side of the arrow. And that's what it looks like for a vector. Sometimes you will see them with just one letter, like we could have a lowercase v. There's a little v here. Something like that. Or sometimes we even see them just bolded, which is not the easiest for me to draw up here. That is a V that's bold, okay? Let me try again. That's ugly, but you get the idea. It's a very bold V. Looks like a heart. All right, so on our notation here, your first letter, is the start, or you can think initial. Second is the end. And all right, guys, then your magnitude or length, realize those mean the same thing. Magnitude is just the length of the vector. Notation, there's a couple ways you might see it. It's going to look like absolute value, but it's not. So that's one way. Or sometimes you will see it with like a double done. Those mean the exact same thing. Why there are two notations for the exact same thing, I don't know. That's just what you get. Different books write it different ways. Alright guys, so two vectors are considered equal if they have the same what? What do you think?
Direction.
Direction and? Okay, so magnitude?
Yeah.
Yeah. I always feel like we should watch Despicable Me with the little villain guy who's vector. No? No, you should go watch that.
Yes.
Alright, so let's pick down here which ones are equivalent. Which vectors look like they are the same? I think somebody said it. What do you think? A, B, and V? Yes. So vector A, B. And vector V. Alright, easy enough to pick out the ones that are the same. Everyone understands why vector FE does not also match? Yes, okay. Alright, we're going to look at representing vectors graphically now. So you've got these points P, Q, R, and S, and then O's at 0, 0. We're going to draw these, and then we're going to find the magnitude for each. So first we're going to draw vector QP. So Q is at -2, 1. So go ahead and put a dot there. And P is at 4, 9. So you get to draw. And I would label them, so this was Q, this was P. So you guys remember how to find the length of a line segment? The distance formula, yes. Okay, well, good start.
The square root of x2 minus x1 squared times y2 minus y1 squared.
So close. Plus in between, not times. And it really doesn't matter. You can do x2 minus x1 or x1 minus x2. You're going to square it, so it doesn't. The order doesn't actually matter. All right, so we would be doing then square root. So QP, here's my Q and here's my P. So let's do -2 minus 4 squared plus 1 minus 9 squared. All right, so what's -2 minus 4 squared? Okay, 36 plus 1 minus 9, -8 squared. Okay, 36 plus 64, square root of 100. Okay. What? Sorry. So distance formula. So basically x minus x squared, y minus y squared. The order doesn't really matter. Okay, you guys try SR for me. So make the sketch first. All right, guys, how'd you do on SR? Did you guys end up with 2 root 10? Yes? Anybody not get to 2 root 10? Please ask and have me go through it, but we're all there. Okay? Distance formula, not bad? Easy so far? Yeah? Okay. All right, so there are other ways to, that was representing them graphically. The other way you can represent vectors is algebraically. In terms of its components. So we're going to talk about component form a couple of different ways. This is component form. It's basically the ordered pair, essentially from the origin where it's going. You'll see these 1, 0, and 0, 1. This we think of as I, this we think of as J. We use this for the position vector. And I know you don't really know what that is yet, but we will get to what a position vector is. And orthogonal is the word we use for perpendicular vectors. So eventually you'll be able to prove whether vectors are orthogonal or not. Sorry, let me move it up. Let's turn the page. All right, guys, so we have a new vector here, vector B. We have point P at 3, 2, point Q is at 5, 6. So I want you to go ahead and graph the vector PQ. So we'll plot our points here. Graphed it. To find the position vector for the second part there, what you're basically doing is finding the change in x and the change in y from one point to the other. So the way, I'm going to go down here just so we have more room. So to find our position vector here, we've got this AI and then BJ part. Your A is just, you can think of it as A2 minus A1. And this is really simpler than it looks. So what were my X's? What's my, essentially my X2 and my X1? Okay, which one do you think is the second? 5, so you would do 5 minus 3. And what about the B represents the Y's? What would those be? So 6 minus 2. So the position vector is just 2I, and these should have little hats on them. I'm always forgetting my hats. Plus 4J. Okay, that is the position vector. form if you wanted to write it in component form. Okay. It looks like an ordered pair, but we're going to use like the angled brackets because you're not just plotting one point. You're saying my change in x is 2 and my change in y is 4. So the component form of this would look like 2, 4. And then the third step says to graph the position vector. So I'm just going to use the corner of my graph here. I'm going to make a new XY axis here. So let's pretend that's X, this is Y. The component form, or I'm sorry, the position vector is just talking about going from the origin instead of just being out in the middle of your grid. So from the origin, I'm going to go right 2 and up 4. So that's your new vector. So your initial point is 0, 0, then over 2, up 4. That is the position vector. Do you guys see how they would be equivalent? They have the same magnitude, they have the same direction. Okay, you're just moving it to start from the origin instead of just starting randomly on the grid.
We have to make a separate graph,
Well, part 3 said graph the position vector.
so you can do it on the big one.
They kind of run into like where I put the P, so that's why I didn't. Okay. Questions so far? It's just you know that that's the position vector, so you know you've changed it now to start from the origin. All right, so let's do example 2. We have a Miss Moy story problem. Her dog Oki starts at his home, which is at point A, picks up his girlfriend, which is 9 blocks east and 6 blocks north. We're going to draw that vector showing his displacement. That just means how far he is from home. Then together they run 4 blocks south, 7 blocks east to the Olive Garden, and share some spaghetti and meatballs. So we're going to draw all of this with vectors. So you get to pick wherever you want A to be. I see from A he's running east and north, so I probably want to start kind of somewhere on the left-hand side of the graph for my point A. So I'm just going to pick, say there's A. That is Oki's home. Okay? So 9 blocks east and 6 blocks north. What does that mean? Yeah, like you're literally just counting 9 blocks to the right and then 6 blocks up. All right, so from there, they've got to make it to the Olive Garden. Where do they go? Yeah, so south 4 and east 7. So you just count down 4. All right, so if I drew in vector AC, that is Oki's displacement from home. And we can also think about vector AC is equal to vector AB plus vector BC. Now we're not saying the total distance traveled is exactly the same, but those two vectors, if you combine the pieces, the components, you do end up with vector AC. We'll talk about vector addition a little bit later. Graphically, not hard to do though, right? To just sketch the vectors, pretty easy. Okay. Are you guys okay with that AC equals AB plus BC, or are we good there? Okay. Okay, so down below, these are just some general concepts for you with adding and subtracting vectors, and also multiplying by what's called a scalar. So if you have two vectors, V and W, and you're adding them together, you really just add the X components together, add the Y components together, and that's your new vector. Same thing with subtraction. You subtract the x's, subtract the y's, and that's your new component. If you have a scalar out in front, that's what this third one is. You just take whatever that number is. So if it's a 3, you take a 3 times the x value, and then a 3 times the y value. That's it. There's nothing tricky with multiplication. The third one there, or I'm sorry, the fourth one, this is just your magnitude again. You can see those little double lines, almost like absolute value. It comes from the Pythagorean theorem that we can just say it's a squared plus b squared.
So that is actually just the first position of them, and then put that in?
Oftentimes it's going to be given to you in the position form. Like I might give you the component, let's say, I tell you, like one vector has, and your other one, we'll call this, well, I'll stick with the V and the W. Okay. And let's say W was -3, 6. Okay? Those are already in position form, in the component form for you. So it's very simple. Like if I said V plus W, you would just go, okay, 2 plus -3, so that's -1, 4 plus 6, 10. Okay? If I said 3 times V, all right, 3 times 2 is 6, 3 times 4 is 12, there's my new vector. So you can represent a vector with just two numbers if it's the component form of the position vector. Does that help a lot? Other questions so far? Doing okay? All right, so if we have a vector that's not equal to 0, the unit vector we can find, it's almost, think of it like if you had a hypotenuse of a triangle and you wanted to turn it into something from the unit circle. If you wanted to make that hypotenuse 1, that's essentially what you're doing. So let me just go through how this works. So let's say, here's my XY grid. Let's say I have some vector V. I know here's 1 on this axis, and here's 1 on this axis. I drew a little arc. It's like I'm drawing the first quadrant of the unit circle there, like that's what that little arc represents. This, I'll go to different colors. That vector in there, that is the unit vector, so it's a vector in the exact same direction as the one you were given, but the magnitude of it is equal to 1. So you're just taking a small section of it. The way you find it, what the formula is telling us up there, it's just the original vector divided by the magnitude. Alright guys, I want you to try the next little section here. You're given vector v and vector w. I want you to find 2v minus 3w. And it says graph both. We're going to graph those together. I want you to do the algebraic part. And then also try to find the magnitude of v. So do 1 and 2 for me, okay? That's where we're going to start graphing from. So just hold on to the graphing. Guys, just do the algebraic part, because we're going to graph it a couple of ways. Guys, what'd you get for an answer to part 1? Two ways you could write it. I would take negative 5i plus 18j, and those should have paths. Or I would absolutely take the component form written this way. How many of you wrote it the second way? Yes? Okay. All right, and then magnitude of this. Did you guys do the nice, easy shortcut? Because let's see, magnitude of v, so just square root of 2 squared plus 3 squared. So 4 plus 9, where we get square root of 13. Yes? Okay, that's just using that magnitude formula. It's really the Pythagorean theorem, just shortened, because you're starting from the origin. Questions on 1 or 2? Anna, can you see it okay? Okay. Yeah. Sure. Let me just go through it.
What was the short way of doing
I just wrote the answer for one,
Oh,
thinking you
okay.
got it, but if you didn't, that's okay. So 2 times v, so that's like 2 times that vector. And then 3 times that vector. Okay. First one's easy because there's no signs to worry about. That just becomes 4 sigma. I honestly would just leave the subtraction sign and multiply by 3. Okay, so then you've got 9 and negative 12. So then when you subtract 4 minus 9, negative 5. 6 minus negative 12 becomes 8. That makes sense? You just mess up a sign. Yeah. Yeah, guys, be careful just with your negatives. You know, nothing new there. Always got to watch out for this. Okay, so let's graph this before we do part 3. So we're going to graph 2b minus 3w, and then we're going to graph also what we would end up with that. So 2v, that means I'm literally going to just count that way twice. So I see v as being the component form here, 2, 3. That means to the right 2 and up 3. Right? Everyone understands that? Okay, so from that point, right 2, up 3. Okay, but it says 2b, so I'm going to do that again. So right 2, up 3. Okay, first part's pretty simple. Then it says minus 3w. So if you look at w, it looks like to the right 3 and down 4. Since it says minus, what do you think I'm actually going to do? Swap them how? Negatively. Like, tell me where I'm going. Right, so you're going to go left 3 and up 4 each time. Okay? That's what the subtraction sign is doing. So, count left 3, up 4. And we got to do that 4 times. Or, I'm sorry, 3 times. Kind of fit on our graph. Hopefully you draw a straighter line from me. Okay?
But if it was plus, you're just keeping going in the same direction.
You would do exactly what it says. You would have gone right 3, down 4. Okay? So, do you see how it says subtract 3w? Okay? That means do the opposite of w 3 times. So since w is really right 3 and down 4, we're going to go left 3 and up 4. Okay? And if you connect your starting point to your ending point here, it's a little rough for me, but hopefully you guys do better. If you counted the displacement here, the change, how far left did we go and how far up did we go? Yeah, and that's what you got when you added it. Okay. Does that make sense? I think that helps make the vector addition piece make more sense to see how it actually works. How is physics going for everyone who's
Terrible.
Awful negative.
See, I get positive when I get like a 60 on the test.
Hey,
No, see, I'm not. But
No,
it's
I'm
not
not.
You don't have to.
I don't. But it's still pretty.
still pretty rough, okay.
Yeah.
Well, maybe a few things will make more sense when we finish this unit.
We should have learned this. Yeah,
Yeah.
I didn't learn this.
We never know.
Should I just change this to the first unit of the year next year so to just help the physics quiz? Yeah, okay. All right, guys. Let's do the next part here. Find the unit vector in the direction of W. So my W, just so I have more room, I'm going to write it, was 3, -4. Okay? To find a unit vector, what do we actually do? We wrote it up above. Do you guys remember? Vector divided by magnitude. Okay, so I've got my vector. I need the magnitude. So how do I find magnitude of this? How do we do magnitude?
Isn't this formula?
Yeah, it's on the previous page. It's guys, it's coming from the Pythagorean theorem. Let me just show you why. So this vector 3, -4. So 1, 2, 3, 1, 2, 3, 4. Okay. If I want to find that length, do you guys see the little right triangle that's there? Okay. This side is 3, this side is 4. How would you find the hypotenuse? I guess -4, sorry. Wouldn't you just do 3 squared plus -4 squared and take the square root? Okay, that's all that formula is telling you to do. And do we know what we're going to get? 5, yeah. Okay, so to actually find our unit vector, there's 2 notations for this. Either one is fine. We can take the component form, so the 3, -4, and we're dividing that by 5, which would give me 3/5 and -4/5. Or if you like the I and the J, so 4. Most people do not prefer the I and the J. Sorry, it's squeezing it in. Why what? I'm sorry.
Why do the I and J have like
Little hats?
yeah?
Because they like to go to a party. I don't know. No, it's just part of the notation.
Are they supposed to be extremely
No, they're like little.
compounds? Doors?
Yeah. They're just like that.
Oh.
I know, this is not the most exciting. We'll get through it. I'm struggling. Yeah.
The I's and J's. Yeah.
It's just talking about, it's so you know it's the position vector. Like, I is like X, J is like Y.
No.
Why we've switched to I's and J's is just vector land. It's what we do. And guys, honestly, you know, we do basics of vectors here. You know, we only spend 2 days on it. Those of you, and we're going to talk course recommendations fairly soon, which is shocking. You guys are going to do course selections like right at the beginning of February, which seems super early. But those of you who are planning to do VC Calc next year and then multivariable calculus your senior year, that's not everyone. That's okay. Saw some scared faces there. You actually do a lot with vectors in multivariable calculus. You don't do a lot with it in VC. Some of you are going to take AB and then BC, and that's great. Some of you are juniors and will take AB, and that's great too. It's completely fine. We'll talk next week, probably next week, about recommendations and where I think you should go and why I think you should go there and where you want to go. Okay. So sort of start putting that in the back of your mind a little bit about what you want to take next year. Okay. All right. Back to the notes here. So it says many times a vector is described in terms of its magnitude and direction rather than its components. So the components were like the little brackets, you know, the 3, -4. That was the components. If we're talking magnitude and direction, we get a little bit of trig involved. So another way to write it, so I could write magnitude of B, and that's the little arrow, sorry, times the direction has to do with cosine and sine, okay? Because it makes sense that it should be related to an angle. Again, we have our I and J because we're looking at the position. So the cosine is always first, the sine is second. Does that make sense to you? The cosine would be where the x component is, and the sine is where the y component is. Yeah, we remember cosine is x, sine is y. Okay. All right, we'll do a little bit more with our cosine and sine here when you turn the page. Okay, so now it's really going to feel like physics. We have a ball thrown with an initial speed of 25 miles per hour at an incline of 30 degrees to the positive x-axis. We're going to express, you're like, no, no. We're going to express the velocity vector. Okay, so we're going to use that formula we just wrote down that talks about the magnitude and it talks about the direction. So my vector, this is the formula I was talking about. You can write it again if you want to. This is yes. It's up to you if you write that. I don't know. All right. This is actually pretty simple. What do you think the magnitude is that we're given?
25.
Yes, the 25. Okay, then an incline of 30 degrees to the positive x-axis. What do you think that is telling me? Right, so like from here we're going up 30 degrees. That's just your theta, okay? The 30 degrees is our theta, so we plug that in. So cosine of 30, sine of 30. You do not need a calculator for this.
Oh, yeah.
Not yet. 30. 30, you know. So what's the cosine of 30? Okay, so it's good I didn't give you a trig quiz today.
It's very good.
Very good, okay. And then what's the sine of 30? Then we are just multiplying by 25. So there's two ways you can write your answer here. I can do 25 root 3 over 2i plus 25 over 2j. Or I would also gladly accept the component form here, 25 root 3 over 2, 25 over 2. Okay, then it's asking us to find the initial speed in the horizontal direction. Do you guys understand, like, if we have a ball thrown and it's at a 30-degree incline, that there's a horizontal piece to that speed and a vertical piece to that speed getting you to that angle? Does that make sense? Okay. Which of these represents the horizontal part? The first one, right? Yeah, the x. So when it's asking you for the initial speed, I'm asking you for that x piece. So 25 root 3 over 2. If you had your calculator and used that, that's approximately 21.651 miles per hour. Okay. What about the initial speed in the vertical direction? 25 over 2, which is 12.5 miles per hour. And guys, think about it for a second. If it's thrown at a 30-degree angle, doesn't it make sense that you'd have more speed in the horizontal direction than you do the vertical direction? Okay, if it was thrown at a 60-degree angle, what would you expect? Yeah, much more in the vertical direction than the horizontal. Okay, so just think about it a little bit. Make sure your answers make sense. Yeah.
It was 45.
They'd be the same. Yes. See, your brain's working now. Okay. Our static equilibrium. We get to go like this. We don't have to do either one. So. All right, guys. So that is the end of your notes. We have a good chunk of time left.
Wow, that's a lot.